So recording is started. Um, Welcome everybody. So the subject of this class is it's electromagnetic theory. So electromagnetism is by far my favorite subject in physics. It's one of those things that every time I teach it, I have a new appreciation for it. It's every time there's a new insight. This is especially true when it comes to physics 610, because that I only started teaching, 3 years ago. I've taught the undergraduate electromagnetism classes many, many times. I've taught it at the 100, 220, 226, 400 levels. I have not taught it at 300 level for some reason. So I've taught it at all these levels. And when we get to physics 610, we can really get to the culmination of electromagnetism, which in my opinion is the relativistic description of electromagnetism. And the beautiful thing is that allows you to start to describe electromagnetism as really two sides of the same coin. But in order to do that, you need to use the theory of special relativity. You should already have learned the the basics of special relativity, E is mc squared and all that jazz. But you might have not used Minkowski tensor calculus before. It is really the most efficient and the most economical, but also the most beautiful, but also the most insightful way to describe things in relativistic notation. There's this beautiful thing that happens when you describe things and you describe how they transform under Lorentz transformation. When you do this properly, you can describe laws in physics that are automatically going to work for you no matter which inertial frame of reference that you pick. So it allows you to describe laws of nature that work in any inertial coordinate system, which is the fundamental thing about the special theory relativity, that the laws of physics should work in a manner that is the same depending on independent on of what inertial frame of reference you have. But in order to do that, I need to teach you a little bit of tensor calculus. This might be new to you. So when we get to that part, it's going to be towards the second half of the semester. I'll go back and we'll do a couple of classes on tensor calculus, the really simple version of tensor calculus. We're not going to throw Minkowski Christoffel symbols. For those of you that have done tensor calculus before, those are not going to show up because we usually don't work with more than curved spacetime. The other thing we're going to do a little bit differently is we're going to skip a lot of the special functions. By now, you should know that if you solve some kind of a wave equation in Cartesian coordinates, you should use sines and cosines. If you do this in cylindrical coordinates, you should use Bessel functions. And if you do it in spherical coordinates, you should also use Bessel functions. And then there's Legendre polynomials and all that jazz. But the thing is, you should know by now that that works for certain geometries. But if I'm going to revisit all those special functions, we're not going to get to the good stuff. And I want to get to the good stuff. So hopefully you'll forgive me that I'm going to skip over all that stuff. The other thing that we're going to skip is contour integration, which is also super useful technology or technique actually, but we're going to skip that as well. Yeah, don't be fooled. We're going to get very, very busy with math. If you need to review stuff, I highly recommend you do. So you should really have your vector calculus and your linear algebra at your fingertips. We'll do some math review. So hopefully you'll see all the concepts that we're going to need at least a couple of weeks before you actually need them in a physics contest. So it gives you some time to go back to your previous textbooks and find out what is what. Okay, so the book we're using is the is GARG. It's the electromagnetism or electrodynamics in a nutshell. Anyway, it doesn't matter. Something in a nutshell, which is a misnomer because I don't know if you all have the book already. It's far from a nutshell. It's quite the epic volume. It's the reason I picked the book is because it does a couple of things really, really well. When we start doing relativistic treatment of electromagnetism, it is super useful to do this in a so-called CGS or Gaussian unit system. This is a system that you probably have not seen before. It is not complicated. It just means that instead of meters, you use centimeters, and instead of forces in newtons, you use dynes and all these things. It just means that Maxwell's equations have slightly different prefactors. And the beautiful thing that happens that at some point you set C is equal to 1 when you do a relativistic treatment, and then the E field and the B field have exactly the same magnitude. You know, when you have electromagnetic waves, there's always this factor of C between the two amplitudes. That is no longer a problem when you have when you do this in CGS, and it's the way that that most theoretical physicists will do electromagnetism. So you should see it sometimes. You should be able to do problems with it. That is to say, I mean, it's not necessarily wrong to do SI. And in fact, there will be large parts of the class that we will do in SI units. So for instance, we'll do some circuit theory. Okay, so the class is structured as follows. So we do the relativistic treatment / Minkowski tensor calculus treatment of electromagnetism. We'll do that towards the second half. The first half of the class we'll do we'll start with Garg's book. We'll follow it mostly as the book is written, but we'll skip around a little bit. The chapter schedule should be posted on Canvas. If you haven't seen it yet, should be very straightforward. Then at some point we're going to make a little detour and we're going to do circuits. Now I'm an experimentalist, so I do circuit theory all the time. And so I have my own particular way of doing circuits, and I want you all to learn how to do it. When we do circuits, we will jump back into the SI coordinate system, unit system, because that's just the way things usually work when you do experiments in a lab. You know, you get things in volts, not EMUs or whatever the units are in the CGS system. And then we'll do phasors and impedances and all that good stuff. And then towards the end of the class, we'll do a couple of selected problems that I think are really, really interesting in electromagnetic theory. There is, for instance, there's this electrochemical impedance circuit element that shows up when you do circuit analysis of electrochemical solvents that are reacting at the surface of an electrode. And you can describe the current voltage response with an impedance that looks nothing like the impedance of capacitors or resistors. In fact, it's sort of in the middle. We'll do that. There's a couple of parts from Feynman's lectures on physics that we will do. There's the AC charging capacitor that is beautiful. There's also the other part we'll do from Feynman is this. There are a couple of these problems that are very nice. When you take a Laplacian equals to 0 for the scalar potential, you can solve boundary volume problems in electrostatics. But it turns out that differential equation maps really, really well onto certain other problems. So you can take a problem that has a solution in electrostatics and you can map it straight onto other problems. Let's say ions in solution, or you can map it onto heat flow in diffusive heat conductors, or you can map it to the displacement of a membrane under tension. So there are a couple of these really, really cool things that are tangentially related to electromagnetic theory that we will also get to, and that will be towards the end. So towards the end, we usually have a couple of classes of buffer space. So if there's a specific subject that you would like me to touch on, a certain part of electromagnetism that you want me to go back to, I'd be happy to do so. All right. Electromagnetism. A review. So The easiest way to get started with electromagnetism is traditionally with electrostatics, right? So in electrostatics, you have this situation oftentimes where you have some kind of a charge, some kind of a Q, and you have some other kind of a charged object, some Q2. And if these guys are both positively charged, then there is a repulsive interaction. So for instance, this guy is positive, this guy is positive. There's a repulsive interaction, which means that there's going to be a force on this charged object due to the object on the other side. And there's another one like this. And we say, of course, because the force in electrostatics is a central force, we say that the sum of these two is the same, or in other words, if I reverse the indices, I just pick up a minus sign. And of course, in electrostatics, we have this really useful description of the interaction between these charges, and we say rather than describing electrostatics in terms of Coulomb force pairs, we say that in between here there's an electric field. So usually what we'll say is the charged object number one, for instance, is the object on the left. It will generate some kind of an electric field. So these are the field lines, and then this will be the field due to object number one, and it will be some kind of a function of position. And if this is statics, because I said it's statics, there's no function of time. And then when we place object two in it, we get a force on this guy, which is going to be just whatever Q2 is times the E field due to number one at the location of charged number two. So all good so far. This is just the way we generally deal with electrostatics, because it turns out when you use Maxwell's equations, it's much easier to first find the electric field, and then afterwards just multiply by Q once you have figured out what your field is. Of course, the electrostatic field is this E field. It is in general a function of both space and time. And most of the time, I will not describe it explicitly as a function of space and time, with arguments in parentheses, R and T. Most of the time, I will just leave it as some kind of a vector field. Now, it is a vector field, so the E field vector field, which means that fundamentally it's a vector, which means it has a thing that points in space, that has direction as well as a magnitude. And in general, in Cartesian coordinates, this could be X, Y, and Z coordinates. And then, of course, because it is a function of both space and time, we call it a vector field. And of course, the vector field is, it's a vector that varies as a function of where you are in space and time. So counterexample. The potential, which could be a function of R and T, this of course is a scalar field, right? Because it's a scalar thing. It could be positive, could be negative, but it certainly does not have direction. Okay, so that's electrostatics. And then of course, magnetostatics. We do something similar. We say, well, the fundamental building block is a current carrying wire. So let's say I have some kind of a current carrying wire. This is my wire number one. And I'm going to put wire number two here. And then we know that the current carrying wires interact because there is a magnetic field in between. So there's a magnetic field here somewhere, some kind of a B, which is a function of R and T. And the magnetic field is, of course, also a vector field. So there's 3 components to vector. And once you have some kind of a description what the magnetic field is, you can find the force on the current carrying wires with the Lorentz force. Okay, now let's talk a little bit about the nature of the field. So most of you know already, hopefully, that electromagnetic fields when quantized, oops, consist of little packets of energy, and those little packets of energy, we call them photons. Now, photons are, of course, not fermions, they're bosons, which means that they can occupy the same state without violating laws of symmetry. Why is that important? Well, it means that once a magnetic field is created by some kind of an object, I can take another object, put it next to it, get the field that it creates, and these fields, we can just treat them independently because these photons, they don't collide, they don't try to sit on each other's, step on each other's toes. And because they don't step on each other's toes, because they're bosons, that means that the field, the source field relation is going to be linear. Okay, what do I mean by that? So the photons can occupy same space. Occupy same states. So therefore, E&M is a linear theory. Okay, so what do I mean? Well, let's start with Gauss's law. So Gauss's law says that the divergence of the E field is 4 pi rho. Okay, this is of course in CGS. So in SI units, it's the divergence of E is rho over epsilon naught. So this is in CGS. And CGS is named CGS because it's centimeters, grams, and seconds. Those are the fundamental 3 units. Okay, so what do we mean by it's linear? Let's say I have some kind of a situation. I have some kind of a red object, some red charge, and it generates a field that I'm going to call the red field. So that means that these things must behave according to Gauss's law. So if I then afterwards have some other kind of a object, and it's a green object, which also creates some kind of a field, which we're going to call the green field, then it too must obey Gauss's law. So if we want to know what happens when we have both, we need to add these 2 together, and you will find that the divergence of the E field is going to be E. Oops. Four pi. So we can describe the field due to a set of charged objects as the sum of their individual fields. And that is because the equations, Maxwell's equations, are linear equations, right? So this would not work if, for instance, there had been some kind of a square here, because if you take a square, you're going to get cross terms, and then it wouldn't work. The superposition principle wouldn't work anymore. So fortunately, that's not the case. So it's linear. Oops. It's a linear theory. Okay. Maxwell's equations. Okay, so first, of course, we have Gauss's law. It is my personal favorite of the Maxwell's equations. In the CGS formulation, the formulation is that the divergence of the E field is given by 4 pi rho. And of course, rho could be a scalar field, right? It could be some kind of a density distribution, charged object spread out through space, or could be point charge. So in general, rho could be a scalar field as a function of space and time. And as a result, the electric field would also be a function of space and time. But in general, like I said, I don't write these. I want to make something really, really clear here. So the causality goes this way. What do I mean by that? I mean, this rho creates this electric field. The reason I bring this up is that it is not the only equation that has both a rho and an E in it, but it is the only one that describes how a rho causes an E field. So for instance, if you want to know the force density on a charge distribution in an electric field, you could get, force density would be rho times E, right? So that's another equation that has a rho and an E in it, but that rho and that E are not necessarily causally related. That rho doesn't cause the E. That rho is placed in an E field that has some other unknown origin. Okay, so causality in Gauss's law is, okay, we have a rho and it causes an E field. Now, unfortunately, nature is kind of painful, and it turns out that a lot of these causal relations are actually differential equations. So in order to find, let's say you have some kind of a rho, in order to find the electric field, you need to solve that differential equation, and there's really no way around it. Now, there are many ways to do it, but it's just nature that's being a pain in the ass here that says, you have to solve a differential equation, even though, if you wanted to do something, you would like to say, I have this rho, I'm going to stick it into a thing, and then out comes an E. So the only way to do that in a very straightforward manner is through direct integration, which is using basically the Green's function of the electric field. Okay, so a rho that generates an E field. Okay, so this describes rho, oops, let's keep it like this. Rho causes an E field. Okay. Second, by the way, there's really no consensus on the numbering of Maxwell's equations. This is my particular preferred order. Faraday's law. So in the full form, the Faraday's law describes that if you have some kind of a time varying magnetic field, then this is dB dt. Causality goes this way again. So you have a causality goes this way again. So you have some kind of a dB dt, and it causes an E field. So there are, according to these two laws of electromagnetism, there are two ways in which you can generate electric fields. You can generate them through changing the magnetic field, and you can generate them by putting some kind of a charged object in space-time. Faraday's law has of course, a special case, and that is the circuital law. So the special case. Circuital law. So it's when dB dt is 0. So then it just says that the E field, the curl of it is 0. And the fact that the curl is 0, that means that the E field is a conservative field. And what do we mean by conservative field? It means that the electric field is a function of position only, and it is not a function of how the charge configuration was arranged, which one came first. It also means that if you can take some kind of a closed path through an electric field, then the work done is going to be independent of the path taken. And in fact, if you get back to the starting position, the total work done is going to be 0. Those are all encoded by the fact that that curl of E is 0. And you should have heard this before. Okay, next one. Gauss's law for magnetism. Okay, running into my own writing. So Gauss's law for magnetism, it's basically the same Gauss's law, except now for magnetism. So left side is the divergence of B, but the right side is, well, what is it? Show of hands. Who knows the answer? Go for it. Ishay? Oh, dude.
I was going
go with 0.
It is 0.
0. I was trying to show a 0 with my hand, but
oh, okay. All right. So it's 0, and it's a big deal that it's 0, because if there were a thing called a magnetic monopole, then of course the right hand side would be some kind of a magnetic charge density. But there is no magnetic monopole. There's only magnetic dipoles, and as far as we know. So the consequence of this, and which is kind of a profound statement, the consequence of this is that there are no magnetic monopoles. Famous counterexample, there was an experiment where people, people with a lot of patience, they look for these kind of things and they try to find signatures of magnetic monopoles, and there's only one recorded signature. It was a weird transient in some kind of a detector, and as far as we know, that's the only one recorded. So for all intents and purposes, as far as we understand the laws of nature, there is no such thing as a magnetic monopole. But if they do exist, they are incredibly rare. Or perhaps they don't interact with, fermionic right-handed matter very well. Okay. So fundamentally, the reason that this thing is zero is not just that there are no magnetic monopoles, it's also that current carrying wires can be the only sources of magnetic fields. So current carrying wires can only be sources of magnetic fields. The only way you can get a current is by making charges move. So fundamentally speaking, magnetism shows up when you make charges move. If you make the charges stop, then the magnetism disappears. So fundamentally, the reason why we have magnetism is because there's this thing called special theory of relativity that says things go a little bit different when you have velocities. So I'll show you why that works, but it's fundamentally, that's the reason why there's no such thing as a magnetic monopole, because the fundamental building block of magnetism is a moving charge. It is just some kind of a current carrying wire, some kind of a charged object that moves with some velocity that constitutes a current. And therefore, because you have a current, you get a magnetic field. Okay, that's fundamentally the only way to do it. Finally, of course, Ampere Maxwell. Ampere Maxwell. So Ampere Maxwell, which says that the curl of B is again causality. Let's make sure we do that consistently. So the curl of B, it's 4 pi over Cj plus 1 over C dB dt. Okay, so what does it say? It says that a J or that's not a B, excuse me, that's an E. A J or a d E dt causes a magnetic field. Okay, without this second term here, it is just called Ampere's law, and this thing is called the displacement current. Oops. Density. Strictly speaking, it's density. And it's, of course, if you got to fix your unit, so there's actually a 4 pi missing here. Okay. So you can actually factor this thing in and write this as, so 4 pi over C, and then J plus 4 pi dE, oops, wrong side. One over 4 pi. Okay, and then you see that this thing looks just like a current, right? So in parentheses, it looks just like a current, and in fact, that is what it is. Now, the reason the term is there is very profound. You need it there because otherwise the continuity equation is not satisfied. And if the continuity equation is not satisfied, that means that charge is not a conserved quantity. And in this universe, as far as we can tell, charge is a conserved quantity. So we'll need this for the continuity equation. And we'll get to that in a little bit. So this is all with sources. And then, of course, without sources, you can see that those right-hand sides, it becomes very, very symmetric. It's kind of nice. And what we mean by without sources, it's a little bit of a misnomer because there are definitely still sources. They're just not externally controlled sources. So there's no rho anymore if you set the sources to 0. And then this guy is just minus 1 over c dB dt. And this is the 0, and then this guy, oops, is just 1 over c dE dt. And then I'll fix this, of course. That's your E. Okay, so looks very symmetric, which is why people looked at this for a long time. They said, you know, why should we treat magnetism differently than electricity? Because once we set the source to 0, the equations are very much the same. So we'll touch on those things many times. Okay, let's do Nearpod. Okay. Derive the wave equation for E from Maxwell's equations. All right, so it's not that complicated. So if you look at this, what you want to do is you want to get a wave equation, which means you want to get something where you get a differential equation only for the E field. So in this case, what you want to do is you want to take a take some kind of an operation that you apply on some of these equations, such that parts of these equations start to look like other parts of the equation, and then you can substitute one into the other. So the most obvious one to do is to just take the, and I think that's actually the only one. So what you do is you take the you just take the curl of Faraday's law. So take the curl here. And that means you take the curl of both the left side and the right side. Okay, so the left side becomes this. So it's the curl of the curl. Now, the curl of a curl is one of those vector relations that you should know as well. So this is just the Laplacian of E minus the divergence of the, the gradient of the divergence, plus the gradient of the divergence of E. This is a vector identity. And of course, the divergence of E, if you do wave equation, this thing is 0. Okay, so the left-hand side is just minus the Laplacian of E. And the right-hand side is the curl of minus 1 over c and then dB dt. And in this universe, we can take partials and we can swap them. We can swap the order. So we could just write this as minus 1 over c ddt of the curl of B. Oops. Of the curl of B. Okay, now the curl of B, in comes to the rescue this guy. So we can write this as 1 over c squared, and then that means we have a double derivative with t, and it just becomes E. And now we have a minus and a minus on the left and on the right. And so finally, this thing, oops, let me just say, this thing disappears, and finally we have the wave equation. E is d squared dt squared, 1 over c squared. Okay, done. Okay. All right, now finally, I want to talk about the continuity equation. Because we will get to it many times. Okay, so The continuity equation, we get it from Maxwell's equations by manipulating Laplacians and gradients and everything. But I don't want to go over the derivation just yet. I just want to show you what it looks like and what it does. So continuity equation, it says that the divergence of the current density is minus d rho dt. Okay, now, show of hands. Who knows what physical principle is encoded in the continuity equation? Interesting. So this is super important. That's why I asked the question. So that means that we should go over a little bit what this means. So it's not immediately obvious when you look at this, unless you've taught this subject 25 million years like I have. So it's not immediately obvious what this thing is supposed to say. So what we do, hopefully you have have already some kind of a Pavlovian response. When you see something like a divergence, you go like, you know what? I know something with vector calculus where I can do stuff with divergences and create surface to volume integrals. So we're going to do that. So what we're going to do is we're going to take a volume integral. So apply a volume integral to the whole thing. So this, and we're going to do a volume integral, dv. The book sometimes does d3x. It's fine, doesn't matter. Okay, so what does that mean? Well, that means we get, on the left-hand side, we get a volume integral of the divergence of j, so dv. And on the right-hand side, we get minus a volume integral of d rho dt dv. Okay, now, left-hand side, we can convert that from a volume integral to surface integral using one of these many Stokes-Green's divergence theorems that I can never remember the name of. So we can convert that from a volume integral to a surface integral. So then instead of this being an integral over a volume V, this is going to become an integral over the surface, which is the edge of that volume V. And now it's a J dot dA. And then the right-hand side is still whatever we had before, but I'm going to reshuffle this a little bit. So there's minus d dt, and this is rho dv. Now, this is, the left integral is a surface integral of the surface that is around the volume in the right integral, because when we started this setup, we took the same integral, that blue integral, we did it. This was identical integral, right? It was the same integral on the left-hand side as we did on the right-hand side. So we're not at freedom or liberty to say that the volume on the right-hand side is disconnected from the surface on the left-hand side. So this is still the integral over the volume, and this is the integral over the edge of that volume. Okay, now let's talk about what that does. So let's say we have some kind of a volume. Okay, now J is a current, and the J, let's say it's an outward flowing current. If we have a current that is net outflowing, that means that there's charge disappearing from the inside. Or, put it in another way, if we have a current going into this volume, then we should get an accumulation of charge. So there's no way in which you can get a current going through this surface without having the charge inside of the volume change. Or, put it in another way, I'm going to put a bunch of charges in a box. Now, ddt of the charges in the box, so this is the integral, this is rho integrated over that volume, this is all of the charge in the box, green box. And we're saying when we take all of that charge in the box, the only way we can have a ddt is if there's a current that goes through the surface that is around the volume. That's the only way in which the charge can change. Why is that? Well, charge cannot spontaneously disappear. If charge could spontaneously disappear, then that right-hand side could be non-zero without a current flowing through the edge. So the only way we can change the current is by physically taking charged objects or charged, things, point charges, whatever we have, and moving them from inside the box to outside the box. And the only way to do that is to get a current that flows from the inside to the outside through the surface that delineates the boundary of the object. So the continuity equation encodes charge is a conserved quantity. And if you take other subjects, there are many of these types of continuity equations that you can find in nature. For instance, you could write an energy conservation law that says that, for instance, you have some kind of an object that has heat in it, and you calculate the total internal heat. So you take the specific heat, you integrate that specific heat over that volume, knowing what its temperature profile is. And the only way you can change it is by getting an outward flux of heat given by Fourier's heat law. So then the continuity equation says, well, the only way in which you change an object's temperature is by getting flow of heat that flows through the boundary of that object. In quantum mechanics, there is a continuity equation that is called the continuity equation for the probability density. And in quantum mechanics, that means that probability is a conserved quantity, right? So we can have weird quantum mechanical superposition things. We can have things spontaneously tunneling from one side to the other, but the probability cannot do weird stuff. The probability current is a conserved quantity. Probability is a conserved quantity. So there's a continuity equation for the probability current that looks just like that differential equation that we had for charge. If you were to say, I'm counting number of cars on the freeway. I'm going to take a segment for the number of cars on a freeway. I want to say in this stretch, let's call it 1 mile. In this stretch of mile long, I'm going to count how many cars there are in this thing. And then after some time, I'm going to count it again. Now, if the number is different, we should do an accounting. We should count, hey, how many cars entered this stretch of highway and how many cars left? And it better be that in the end, if the number has changed, it's because, for instance, more cars left that stretch of the road than have entered that stretch of the road. Because otherwise, cars would be spontaneously appearing or disappearing. And in this universe, that would be weird, right? So I hope you understand that this is a fundamental way of looking at conserved quantities. And hopefully it's your first, but not your last exposure to it.